Okay, let's see some numbers. This is std remove 10,000 bytes integers, so about 2,500 integers. Half of the elements are zeros. We're removing zeros. std remove is completely scalar code. There are no vector instructions. Okay, the difference between minimum and maximum is about 1.5 times. This is by padding. So I presume that we do see the code alignment effects here. Out of interest, I did the same test on std transform. std transform is doubling every element in a vector using std transform. This was a bit surprising. So for SSE2 and SSE4, we get no effects of code alignment visible. However, for IVX2, we see jumping. And this is weird because as far as I know, this is almost 2 times, right? Well, not quite, but 40% difference or something. As far as I know, all of the effects of code alignment come from branches. So, and there are not really branches in SSD transform. It's auto-vectorized, so you have a gigantic wall of vector instructions, and then you jump to the beginning. I tested, as far as I know, I'm not going to go through it, but I got the counters that I know could be affected. And this is a good case. This is a bad case. I don't see any significant difference. I created a Stack Overflow question, and then I think I got it. Right. The thing is that in the first case, the address of the vector, right, is going to be aligned to 32 bytes. And in the slow case, it's going to be aligned to 16 bytes. So STD transform, when it's vectorized, it's actually, you get vectorization, but the compiler will not align data accesses. And so I think this is the price for accessing data in the non-aligned way. We can have another confirmation of this if we look at how if transform behaves for dealing with the in-place vector, in-place case, right? Because for in-place case, we do aligned reads and writes. And then we can see that, hey, there is almost no variation. So presumably, we don't have this issue. I'm still waiting for somebody to give me a good way to confirm it, but if that's really a aligning of data accesses, that would be really interesting. Okay, so given that we have 64 numbers for every measurement, what do we do with them? We pick minimum. Why minimum? Well, for code alignment, I have a really good explanation. It's basically that we can actually align the code ourselves if we really want to, right? And this is in strlen, right? This is a directive to align the following code to 16 bytes. Awesome. With the things that are like we saw just now with transform, where it's just data alignment issue, well, it's still gonna pick min. My reasoning here is that alternative is to try to analyze all of the possible outcomes, and maybe we don't generate enough of data inputs and all that stuff. So it becomes just really, really difficult problem. So I think we should stick with min, and this should be good enough for us. Okay, a couple final things. What cases do I measure? For I measure 40 bytes, 1,000 bytes, and 10,000 bytes, and I measure chars, shorts, and ends. Why not doubles or in64s or floats? Well, the thing is that as is, benchmarks take about 5 hours to run per one configuration, right? So it's just a lot. So I decided to drop some. What about 40 bytes? Why is 40 bytes important? Well, the thing is that I wanted to answer, is the SIMD version of the algorithm always usable compared to the scalar version of the algorithm, right? Like strlen. Strlen is going to be called for every size of the string, even for really, really tiny ones. And so the question is our SIMD algorithm usable like strlen? What about 1,000 and 10,000 bytes? Well, these are still pretty small sizes, but actually behave about the same. So maybe one of them can be dropped. I started like that, so I'm still going. When it comes to measuring more than 10,000 bytes, it's a bit of a question. I generally believe that Small sizes are more important than large sizes. They're much more common, at least in my work experience. I always dealt with small sizes. Maybe they come on a really high rate, but still small sizes of data. I oh, but when it comes to also the big sizes, alternative tools you can use, like if you talk in megabytes as GPUs, and I don't know anything about GPUs, but I believe this should be easier to program and they have wider SIMD. Or at the very least, you probably for a large chunk of data you will use multiple threads, right? And so, given that you're using multiple threads, how much data do you get per thread? Nevertheless, there are probably some interesting information you can glimpse from measuring bigger data, but I have some limited compute resources, so this is what I'm sticking with. And that's it for today.